In this example, we're going to use a comparison test to help us determine whether the following series converges or whether it diverges. And what I'm going to highlight in this example is a case in which the limit comparison test actually can't help us draw a conclusion. So we're going to go back and try setting up an inequality to directly relate our series to one that we're comparing ours to. So let's go ahead and check it out. So with any of these comparison test problems, the first thing that we try to do is find a series to compare to. So we take our series function, the 1 plus, in this case, sine of n, all over e to the n. And we can ask ourselves questions like, what term contributes the most in the numerator? What term contributes the most in the denominator? Asking ourselves for large n, what terms matter the most? How big can the numerator look? How big can the denominator look? And well, if we start off with these types of questions, well, there's one term in that denominator, the e to the n. So we're just going to pull that to the right-hand side. Now, if we look at this numerator, well, if we ask ourselves the same question, who's contributing the most for very, very large values of n? Well, the 1, that's always a 1. This sine of n, the largest that thing is ever a 1 as well. So we could kind of make the connection of how large could this numerator ever be? Well, it could ever be as large as 1 plus the largest sine can be, which is also 1. So the largest that numerator could be, we could think of that as a 2. So the series we could compare ours to could be for the series from n equals 1 of 2 over e to the n. And while if we're looking at this, we're going to ask ourselves next, what does this series do that we're comparing to? So we can take a look at this series. The series, again, n equals 1 to infinity, 2 over e to the n. And well, what we see in this series is that we have constants raised to powers of n only. So what I mean by that is this is actually going to be a geometric series in hiding. So we can write this series in the following way. From n equals 1 to infinity, we can look at this like 2 times 1 over e to the n. And we can get this into a little bit more familiar geometric series form by writing this as 2 times 1 over e, that whole thing raised to the nth power. Because in the numerator, well, a 1 to any power n, that's still a 1. So we could take the 1 over e and raise that whole thing to the nth power. And to get this into the real familiar geometric series form, we can factor out a 1 over e. So we have a 2 over e now, times the 1 over e raised to the n minus first. And for us, what really matters for a geometric series is identifying our r value. And for a geometric series to converge, what we need is the absolute value of r to be less than 1. In this case, we have the absolute value of r is equal to 1 over e. Remember, e is about 2.717, a whole lot of change after that. So this thing is indeed less than 1. So the series we're going to try comparing to, it converges. Which brings us to the choice of, once we've had the series we're comparing to, once we know that series converges or diverges, we can either go down the limit comparison route or we can try setting up an inequality. And what I just want to show us first is what happens if we try the limit comparison route on this problem. So for the limit comparison test, we take the limit as n goes to infinity of the ratio of our series functions. In this case, we have the ratio of 1 plus sine of n all over e to the n. And the series we're comparing to, which was the series 2 over e to the n. And for the limit comparison test to tell us anything, we need that this limit is a finite non-zero number. If this limit turns out to be a finite non-zero number, limit comparison test says, hey, both series do the same thing, as in both series converge or both series diverge. Well, let's take this limit before we get ahead of ourselves. So we have this limit as n goes to infinity. We're dividing by a fraction, so we can reciprocate and multiply that fraction on. So we have 1 plus sine of n all over e to the n. And we're multiplying that by, well, the reciprocal of that denominator, which is e to the n over 2. So those e to the n's, they cancel out. This limit is looking like it's simplifying a bit for us, but in the next statement, we're going to run into some trouble. We have 1 plus the sine of n all over 2. And well, as n goes to infinity, one of the issues is this sine of n function, that is always going to be varying. That's always going to be some number between -1 and 1, as n just keeps growing and growing and growing. And because of this, this limit is never going to settle down to one specific value. So this limit actually does not exist. This limit does not come out to one finite value, one infinite value. This limit is always going to be changing values because as n gets larger and larger, this sine of n is always going to be a different number between -1 and 1. Maybe it'll repeat itself, but it's never going to settle down to just one thing. So what this means is limit comparison test can't help us. So if limit comparison tests can't help us make a conclusion, the next thing we try to do is directly compare our series through an inequality. So I'll just say, try setting up an equality. And what this means is we want to directly compare our series function that we started with against the series that we know something about. So looking at this, our original series was 1 plus sine of n all over e to the n. And the series we're comparing to is the series of 2 over e to the n. And now the series that we're comparing to, we saw earlier that that series converges. So if we want to draw a conclusion about our series, we need to show that our series is always less than or equal to that known convergent series. Because if we're smaller than a known convergent thing, there's no way for an infinite amount of positive terms to go off to infinity. So again, what we'd like to see from this inequality here is that this left-hand side, our series, each term is always less than or equal to the series that we're comparing to that we're known to converge. Okay, so we want to try and show that this inequality is true. We can cancel some terms off. We can, well, cancel off an e to the n from both sides. Or if you imagine, we cross multiply these e to the n's and divide. So what we're really asking ourselves is 1 plus sine of n always less than or equal to 2. And actually, since we talked about this sine of n term, this is always a number between -1 and 1. So because of this, for any n value, the largest this left-hand side could be is 2. That's the largest it can ever be, which means that left-hand side is always less than or equal to 2. So for any n value, the left-hand side is always less than or equal to 2. So we have shown that our series is less than a known convergent series. So that brings us up to our conclusion now. Since basically every term of our series is less than a known convergent series term, our series must also converge.